Everyone to the afternoon session on web privacy and device tracking. Hope you all had a good lunch. The questions after the talk, please just say them from your seat and our speakers will repeat them for the remote audience. First, we have Ikram, and he's going to talk about towards seamless tracking free web, improved detection of trackers via one-class learning.
Is it okay? Okay. Thank you, Rob. So by one-class learning, today I'm going to talk about our way of improving the detection of JavaScript programs. This is a joint work with under the supervision of my PhD advisor, Muhammad Ali Ghaffar, aka Dali Ghaffar, with Anirban and Hassan and Bala from AT&T Research Lab. So I know that you probably know about web tracking, but let me give you what happens when a browser load requests an HTML source from a web server, in this case like NewYorkTimes.com. So upon executing the initial JavaScript in the HTML source code, browser sends additional requests and loads tons of resources from third-party services in the form of tracking, ads, and pop-ups, and of course some useful resources from CDNs. In this case, it loads ads from Google, and also the execution of JavaScript also sets cookie on user browser, that are used for tracking the user on the web. So ads and cookies and social widgets that are enabled by JavaScript programs tracking user, and one of the speaker on Tuesday pointed out that user normally feel fear and concern about their privacy because these Googles and some other hackers, and in this case our term is trackers, continuously tracking user and enter into user computer and devices and analyze whatever they are doing on the web, and they take a huge amount of data about user online presence. So to ease such sort of fear and privacy concern, of course today we have many privacy preserving tools that are trying to block third-party trackers. These PPT tools are very often use blacklist of URL or patterns of URL. But not all JavaScripts that belongs to a URL or domain are not used for tracking. Some JavaScript could be used for very essential functionality of website. In this case, we can see on the left-hand side that when bright curve is blocked by one of the PPT tool, a privacy-preserving tool, it removes certain essential content from the web, and the video, when it is allowed, the video start working. It means that the essential component that belongs to that website start working. So it means that these privacy preserving tools have very poor uptake, as pointed by one of the recent work they pointed out that privacy preserving tool has its uptake up to 20%. And we believe that this poor uptake of privacy preserving tool is because of their poor imbalance or poor balance between tracking and functional JavaScripts. And we think that blocking of URLs or blocking of URL is not an effective way to block tracking JavaScripts. And in this work, what we did to look into the programs, the JavaScript code itself. And the basic rationale of our work is that tracking JavaScripts are similar to each other and they are distinct from functional JavaScripts. And the rationale behind this is that most often developers use third-party tracking JavaScripts or code that is previously published online for their websites, or like they reuse the code that has been previously published on the web. So it means that our work is somehow similar to plagiarism detection in codes, or like our program analysis that is in the related literature. To give you a basic idea that how tracking JavaScripts are similar to each other syntactically and semantically, let's have this example. You can see that we have two JavaScripts that are setting cookies for two distinct trackers, in this case for Google Analytics and Visual Revenue. From the variable initialization and the functionality to push values into the cookie database, we can see that they are they are similar to each other. Of course, they have some difference or dissimilarity in the way the variables are assigned, or the variable in the case of variable names and the values that is assigned to these variables. And I will show you in a bit that how can we deal with such sort of things, such sort of dissimilarity. In order to show you the similarity of tracking JavaScript and their dissimilarity with functional JavaScript, and to test that whether our statement is plausible, we try to look into the intra-similarity and inter-similarity of tracking JavaScript and functional JavaScript. We can see that in this probability distribution of cosine similarity matrix, we can see that tracking JavaScripts are similar to each other and they are distinct from functional JavaScripts, which is shown in the red curve. So this is the overview of our work. We analyze privacy-preserving tool, and we propose a classification framework that is based on a single partial knowledge of tracking JavaScripts. By partial, I mean that we can take tracking JavaScripts from the previously published list, and we see that these previously published lists are not complete enough, and that's why we think that they are partial and it could be used for training our classifier. So before giving you the result and analysis of our classifier, let me tell you about our methodology, which consists of 4 steps: data collection, feature extraction, and classification evaluation. So we extract DOM trees from web domains when the PPT tool were on and when they were off. We did some manual labeling in order to understand whether the JavaScripts are tracking JavaScript are labeled or functional JavaScripts, which constitute our labeled data sets. We use that labeled data set for our as a ground truth for our classification. And of course, then in feature extraction, we extract features for our classifier, and then we evaluate privacy-preserving tool and validate our classifier. So here are the rule that we basically use for extracting or creating the ground truth the data. These rules are extensively discussed among the authors, and then we applied these rules on the JavaScripts that we extracted from the DOM tree. So for instance, rule number 3 is about all social widgets that we label as the tracking. And similarly, rule number 9 is basically all JavaScript that fetch content from first-party domain or third-party CDN that we label as functional JavaScripts. So let's look into the analysis of privacy-preserving tool. First, we look into the aggressivity of privacy-preserving tools, which we define as the ratio of blocked JavaScripts by a privacy-preserving tool to the total number of JavaScripts in the DOM tree. And here we can see that the aggressivity of privacy-preserving tool increases from left to right, and NoScript in this case is the most aggressive one, while Privacy Badger and Disconnect are the least or the less aggressive of the PPT tool. Then we look into the effectiveness of privacy-preserving tool, which we define as the balance between correctly blocking tracking JavaScripts and incorrectly blocking functional JavaScripts. So here is a little breakdown of the effectiveness of privacy-preserving tool. So we can see that NoScript, which has the highest true positive rate of 78%, blocks 1/5 of the JavaScripts that are used for essential functionality. On the other hand, Privacy Badger, which has very good false positive rate, but it allows a huge amount of tracking JavaScripts, and it overlooks a huge amount of tracking domains or JavaScripts. So before going to explain the classification framework, let me briefly explain the feature extractions. Of course, we know that JavaScript may have like very complex statement. We used the previous work in order to convert this complex JavaScript into simple programming statement that we call canonical form, and from the canonical form we extract program call dependency, data dependency graph, and then we calculate n-gram matrices on the program dependency graph. In addition to program dependency graph, we also extract sequential sequential n-gram, which is based on the canonic sequence of extraction in the canonical form. And to find out the relative importance of n-grams, we use TF-IDF measure. So I don't have like too much time to go to the nitty-gritty detail of one class SVM. For detail, you can consult our paper, or you can look into the references which are given here. So the juicy part about these one class SVM, one class learning is that it could be trained with only one class, and it classify new data depending upon, or test data depending upon its similarity to the trained data or its dissimilarity. So here is a little bit breakdown of our classifier performance. As you can see that our classifier achieved more than 99% of accuracy with less than 1% of false positive rate, and it improves the accuracy of privacy preserving tool up to 63%, and it reduces the false positive rate up to 20%. Let's apply our classifier on the wild data set. Since we don't have like ground truth for the whole wild data set, we look into the dissimilarity of our classifier output and that of the privacy preserving tool. So in this case, you can see we turn the agreement between our classifier output and data privacy preserving tool in green. Here the term T means tracking and C means the classifier. So what is being labeled by our classifier is tracking, and what is being labeled by privacy preserving tool is tracking. And similarly, like functional JavaScript and that is labeled by our classifier is functional one, and that is labeled by privacy preserving tool is functional one. We also look into the dissimilarity or like disagreement, which is shown in color in red. So here is the plot. Here is the agreement and disagreement of our privacy preserving our classifier in in the privacy preserving tool. So we can see that our tool has the highest agreement in terms of true positive with no script, and it has the highest disagreement with disconnect and privacy badger in terms of false positive. We dig into this disagreement and we analyze that. We try to look into these disagreement and to know about whether our classifier was right or the privacy preserving tool were right. So we look into the JavaScript that our classifier label as tracking, while all PPT tool considered as a functional one. And similarly, we look into JavaScripts that our classifier labels as functional and all PPT considered as tracking. So we from this we have like a set of more than 4,000 JavaScript. In both the cases, we randomly select 100 samples out of these samples and apply our manual labeling upon them. And in this graph or in this table, we can see the color in green is when the manual labeling agrees with our classifier output, and the color in red shows when our manual labeling disagree with our classifier output. So for the 75% of the cases, our classifier was right, and for 25% it was wrong. And the reason that the privacy preserving tool disagree with our manual labeling and classifier is that privacy preserving tool perform regular expression on the URL in the script tag and fail to detect tracking JavaScript that are not in the blacklists. So, and for the 81% of the case, our classifier was right. And the reason that when privacy preserving tool were not right is that privacy preserving tool blocked JavaScripts from tracking domain, even though some JavaScript perform useful functionality. So stressing again here, if you look at both the cases, the performance of our classifier is extremely high if we consider a disagreement with all privacy preserving tools. So in the process, we find out some new tracking domain, more than 4,000 tracking domain. For instance, in this case, like we found out that the JavaScripts on Telegraph and the JavaScripts on IYE.com is basically tracking user and shows an advertisement to the user and perform analytic services. There are further detail about our work, the limitations, certain limitation in case of the obfuscation of JavaScripts, and And further analysis of our approach is given in the paper, and I recommend to read our paper for further detail. So in conclusion, what I have shown to you that the existing privacy preserving tool based on regular expression on the URL or the patterns of URL are ineffective. When they are very aggressive, they are blocking functional JavaScripts, and when they are least aggressive, they overlook a huge amount of tracking JavaScripts. And with this new framework that we design in our paper, in our work, which could be trained with only one single class, and I have shown to you that how can we train that classifier and which can achieve validity accuracy up to 99%. And of course, we in the process we can discover more like trackers that were previously unknown to the privacy preserving list or to the blacklist services. With that, I would conclude my work, my presentation, and I would thank to Pete's reviewer who improved this paper and gave some very valuable suggestion on our work. Thank you very much, and thank you for your attention.
We have time for some questions. I'll start off with one from